Okay, so in this section, right, we're learning all about functions. And on Wednesday, we learned how to find the domain of a function. Okay. There are two situations we have to be concerned with. When we have x in the denominator, we have to concern ourselves with those values of x that make the denominator equal to 0. And those values of x that make the denominator equal to 0 are not in the domain. And then in the second situation, right, where we have a square root with x under the square root, we have to concern ourselves with those values of x that make the radicand, right, it's called the radicand under the radical. Those values of x that make the radicand negative, right, the value of the radicand negative, and those values, the square root of a negative number, it's not a real number, it's an imaginary number. And we're only interested in those values of x that make the value of the function a real number, not an imaginary. And so we have to concern ourselves with those values of x that make the radicand negative. Okay? Those numbers are not in the domain of the function. Okay? All right, so if you flip over to page 4, we're going to review the vertical line test, which I remember from my high school days. So remember, an equation is just a relationship between the variable y and the variable x. And the variable y we often refer to as the dependent variable. Or output variable. And x is the independent variable. Or the input variable. So here we have the graph of 3 equations. Remember, the definition of a function is for each input, x, there is one and only one output, y. Okay? Can't be 2, can't be 2 y's, 3 y's, 4 y's, 5 y's. There's going to be one y. For each x, there's going to be one y. Okay? And so given the graph of an equation, you can tell, with the vertical line test, whether for every value of x, there is only one and only one value of y. Okay? And so the idea is, right, given the graph of the equation, between y and x, you can draw the vertical line. No matter where you draw the vertical line, if it intersects the graph in only one location, that means for each value of x, there's only one value of y. So for this value of x on the x-axis, there's only one point on that graph, and that's the value of y. There's one value of y. For this value of x, there's only one value of y. For this value of x, there's only one value of y. So this equation, okay, meets the definition of a function. Right? Y, the variable y, is a function of x, because for each value of x, there's only one value of y. Okay? Over here we have the graph of a circle. Okay? You know the equation of a circle. And this one, right, centers at the origin. And you can see that when I draw the vertical line here, for this value of x, there's 1, 2 values of y. So this is not a graph of a function. Okay? Y is not a function of x in this case. Because this value of x, we have 2 values of y, we can only have 1. this example over here, okay, y is not a function of x, because for this value of, did I say for this function over here? I didn't mean to say that. For the graph of this equation over here, y is not a function of x, because for this value of x, there's 1, 2, 3 values of y. And you only have one value of y for each value of x. So y is not a function of x in this case or in this case. Right? In this case, there are two values of y for one value of x. In this case, there are three values of y for one value of x. Right? There's going to be one value of y for each value of x, for y to be a function of x. Okay? All right. So that's the vertical line test. So an exercise down below says use the graph of the function f given below to answer the following questions. So here's the x-axis, here's the y-axis, and each rectangle is 2 units. So you can see going from here to here is 2 units on the x-axis. So this will be x equals 4, this will be x equals 6, this will be x equals 8, x equals 10, x equals 12, right, on the x-axis. Similarly on the y-axis, right, each rectangle is 2 units. So it's 2 units from here to here on the y-axis. So this would be y equals 4, and this would be y equals minus 2 down here. Now, remember, y values and function values are the same thing, right? That's why we write y equals f of x. Okay? For each value of x, right, y is equal to the function value. That value of x. So in A, you're asked to find the value of f of 2, right? 2 is the value of x. Okay. Well, f of 2 is equal to the value of y at x equals 2. So you go over here to the graph. Here's x equals 2. And here's the point on the graph with 2 as an x coordinate, and the coordinates for that point are 2, 4. Right? 2 is the x coordinate, 4 is the y coordinate. So f of 2 is equal to the y coordinate, which is 4. The value of the function at x equals 8. So you go to the graph. Right, here's 8 on the x-axis. Here's the point on the graph at x equals 8. And the coordinates for that point on the graph are 8, minus 2. 8 is the x coordinate, minus 2 is the y coordinate. And so f of 8 is equal to the y coordinate, which is minus 2. Function values and y values are the same thing. Okay. Any questions on that? All right. In B, it asks for what numbers x is the function equal to 2. Okay. Well, another way of asking that is for what numbers x are there y coordinates equal to 2? Okay. So come over here to the y-axis. This is y equals 2 on the y-axis. Okay. So what number is x? Is f of x equal to 2, which is the same as asking for what number is x is y equal to 2, right? Is the y coordinate equal to 2? So here's the y-axis, and you can see going to the starting at y equals 2, there are 2 points on the graph with 2 for a y coordinate. point right here, which has coordinates 0, 2, right? The x coordinate, any point on the y-axis has 0 for an x coordinate. So that point is 0, 2, right? It's also the y-intercept. And then this point right here, right, is above x equals 4 on the x-axis. And so it has coordinates 4, 2. So the 2 points on the graph that have 2 for a y coordinate are the points 0, 2, and 4, 2. And the x coordinates, right, for those 2 points are x equals 0 and x equals 4. So the answer is x equals 0, x equals 4. So that's also saying f of 0 is equal to 2 and f of 4 is equal to 2. Okay. What is the domain of f? Okay. So we did this earlier. The domain, right, given the graph of an equation, okay, the domain is all the x coordinates. Well, you can see that this graph starts here on the left, and then it continues continuously to this point on the right. And so this point on the left has an x coordinate of 0, and this point on the far right has an x coordinate of 12, right? This is the point 12, 0. So the domain is all the x coordinates. So there's no breaks or jumps in this graph. And so the x coordinates go from this point, which is 0, to this point, which is 12, right? So x equals 0 at this point, it equals 12 at this point. And so the domain in inequality notation is x is greater than or equal to 0 and less than or equal to 12, which in interval notation, bracket 0, 12, bracket. So every number from 0 to 12 on the x-axis, for each of those numbers, for every number between 0 and 12 on the x-axis, there's a point on the graph with that number for an x coordinate. That's the domain of the function. That's the input to the function. The range is the y coordinates. So the lowest point on the graph is right here. That's 0.8 minus 2, right? Minus 2 is the y coordinate. And the highest point on the graph is this point right here, which has coordinates 2 and 4, right? 2 is the x coordinate, 4 is the y coordinate. And so the graph, this function is continuous, right? There's no breaks or jumps in it. So the range for this equation starts down here at y equals minus 2, and it goes up to here to y equals 4. So for every real number from minus 2 to 4 on the y-axis, there is a point on the graph with that number for a y coordinate. So the y coordinates start down here at minus 2, and they go all the way up to plus 4. Okay? So you go from the lowest point on the graph to the highest point on the graph to get the range. What is or are the x-intercepts? Well, x-intercepts are where the graph crosses or touches the x-axis, right? So where does this graph either cross or touch the x-axis? for what values of x? Well, 1 is 6, right? It crosses here at x equals 6. So x equals 6 is an x-intercept. And it touches here at x equals 12. So x equals 12 is the other x-intercept. X-intercepts are where the graph crosses or touches the x-axis. The y-intercept is where the graph crosses or touches the y-axis. So looking at the y-axis here, you can see there's only one point where it touches the y-axis. It's this point right here. And the value of y on the y-axis where it touches this 2. So y equals 2 is the y-intercept. Okay. Now if you want to, right, you can write the x-intercepts as an ordered pair. Right? So x equals 6 and the 0.60 are the same. And x equals 12 and the 0.12 are the same. And with the y-intercept, y equals 2 and the 0.02 are the same. All right, any questions on that? All right, for what numbers x is the value of the function less than 0? Well, where the value of the function is less than 0 is where the graph is below the x-axis. So remember, function values and y values are the same. So where the function values are less than 0 is where the y values, the y coordinates are less than 0. Well, here's the y-axis, and the y coordinates, right, negative y coordinates are down, right? This is the negative part of the y-axis where the negative numbers are. And so the part of the graph that's below the x-axis, all the points on this part of the graph have a negative y value for a y coordinate, right? The negative number for a y coordinate. So where the value of the function is less than 0 is where the graph is below the x-axis. Well, we want to know for what numbers x is the graph below the x-axis. Well, it starts here at x equals 6, and it ends over here at x equals 12, right? From x equals 6 to x equals 12, the graph is below the x-axis, which means the value of the function is less than 0 for those values of x. So this is strictly less than 0, not equal to 0. At x equals 6, the value of the function is 0. At x equals 12, the value of the function is 0. So the answer is for x strictly greater than 6 and less than 12. So that is the answer in inequality notation. The answer in interval notation, parentheses 6, comma 12, right parentheses. This is interval notation. One thing you got to be careful about in math is we use the same notation for interval notation and for a point in the coordinate plane. So this right here, 12 comma 0, that's a point in the coordinate plane. This right here is an interval of numbers. And we use parentheses for both. So you got to know what context that notation is being used in, okay? Otherwise you can get confused. In H, it asks for what numbers x are the values of the function greater than 0. Well, that's like asking for what numbers x are the y coordinates greater than 0, right? Or what numbers x is y greater than 0. Well, that is where the graph is above the x-axis. Where the graph is above the x-axis, okay, all the y coordinates are greater than 0. Well, you can see that's where the graph is above the x-axis. Starts here at this point, and it ends right here at x equals 6. So we're doing strictly greater than 0. So this point here is strictly above the x-axis, and its y coordinate is 2. Excuse me. It's asking for what numbers x is the function above the x-axis. So 2 is greater than 0, okay? And the x coordinate for this point is x equals 0. And the graph is above the x-axis until we get to this point, x equals 6 on the x-axis. But at x equals 6, the graph is, the function is equal to 0, not greater than 0, right? That's an x-intercept. And so x less than 6. You can't include 6. So from x equals 0 up to x equals 6, the graph is above the x-axis. Right? Those are the values of the function that are greater than 0. Okay? All the y coordinates are greater than 0. And so in interval notation, the numbers x for where the function is greater than 0 is bracket 0, comma 6 parentheses, interval notation. Okay. Any questions on that? So now you have everything you need to successfully complete the MyMathLab, or not the MyMathLab, the website. All right, so now we're going to talk about graph symmetry. This is the short section, 23 pages. All right. So there are 3 kinds of graph symmetry we're going to discuss. And the 3 kinds are called y-axis symmetry, x-axis symmetry, and origin symmetry. And the first one we're going to discuss is y-axis symmetry. And so here is the graph of an equation that demonstrates y-axis symmetry. Okay? And this is actually a parabola. Okay? You may recognize it as a parabola. And if the graph of an equation demonstrates y-axis symmetry, the part of the graph to the right of the y-axis is a mirror image of the part of the graph to the left of the y-axis. Okay? If we could fold this, right, fold your paper right here on the y-axis, you could fold the right half of the graph directly on top of the left half of the graph. That's y-axis symmetry. Okay. Now, a graph that demonstrates y-axis symmetry, it's true that for any point on the graph, like the point 24 here, if you change the sign of the x coordinate, that point is on the graph. So if we change the sign of the x coordinate here, right, this is the point 24. So if we change the 2 to -2, then the point -24 is on the graph. Okay. Up here we have the point -39. If we change the sign of the x coordinate from -3 to +3, then the point 39 is on the graph. Okay. So if the graph of an equation demonstrates y-axis symmetry, if you change the sign of the x coordinate of a point on the graph, then that other point is also on the graph. Okay. All right. Given an equation whose graph has y-axis symmetry, you can test that equation for y-axis symmetry by switching. This is the third rule here. By replacing x with -x in the equation, and if you get the same equation after you get the original equation after you simplify, then the graph of that equation will have y-axis symmetry. So we'll demonstrate that with this equation down below. We have y cubed is equal to x to the 4th plus 5. This is our original equation. So without actually graphing this equation, we can show that the graph will have y-axis symmetry. Okay? And the first step is to replace x with -x. So y cubed is equal to -x to the 4th plus 5. Okay? And now we got to simplify. And after we simplify, if we end up with the original equation, then we know the graph of this equation will have y-axis symmetry. Okay. Well, -x to the 4th, let's just review this, means 4 factors of -x. Negative times a negative, positive. Positive times a negative is negative. Negative times a negative is positive. So the product of 4, right, even number negatives is positive. And then we have x times x times x times x, which is x to the 4th. So -x raised to the 4th power is equal to x to the 4th. So on the right-hand side, -x to the 4th power is equal to x to the 4th. And that's our original equation. Y cubed is equal to x to the 4th plus 5. So we can conclude, hence, the graph of this equation has y-axis symmetry. Without actually graphing. Okay. Do they still in high school do the 3 dots for hints? Or that might be something from the 1970s. Okay. That's what we used to do. Okay. So if they don't do that anymore, we'll just write out or thus. Okay. All right. So any questions on that? All right, now let's talk about x-axis symmetry. And x-axis symmetry has the same idea, right, as y-axis symmetry. So here's a graph of an equation that has y-axis or x-axis symmetry. So here's the x-axis, and notice that the top half of the graph is a mirror reflection of the lower half of the graph. Okay. So if you can take your paper and fold it along the x-axis, right, you could fold the top half of the graph directly on top of the bottom. Okay. That is x-axis symmetry. Okay. And x-axis symmetry also has the characteristic, graph from the equation of x-axis symmetry, is you take any point on the graph, like in this case 4, 2, and you change the sign of the y-coordinate, that corresponding point is on the graph. So here's the point 4, 2, right? 2 is the y-coordinate. I changed the plus 2 to a minus 2, and you notice that the point 4 minus 2 is on the graph. Okay. Similarly, this is the point 9 minus 3. And so, right, 9 is the x-coordinate, minus 3 is the y-coordinate. And so if I change the y-coordinate from minus 3 to plus 3, then that point 9 plus 3 is on the graph. Okay. So if you change the coordinate, you change the sign of the y-coordinate for any point on the graph, then that corresponding point has to be on the graph. Okay. All right. Now, given an equation without actually graphing it, you can determine whether the graph of the equation will have x-axis symmetry or not. So here we have, right at the bottom of your page, we have x equals y squared. And to determine whether the graph of this equation has y-axis symmetry, or x-axis symmetry, we replace y with negative y, and then when we simplify it, we end up with the original equation. We know the graph will have x-axis symmetry, even though we haven't graphed the equation. So first step, replace y with minus y. And so we have minus y squared. You know, minus y squared is minus y times minus y. Negative times negative is positive. And y times y is y squared. So minus y quantity squared is just equal to y squared. And that's our original equation. conclude the graph of this equation has x-axis symmetry. Okay? Even though we haven't graphed. Okay? That's how you test for x-axis symmetry without graphing the equation. Okay? Any questions on that? All right. Then the last form of symmetry is origin symmetry. Turn to page 3. And origin symmetry, if a graph has origin symmetry, you can take the graph, turn it upside down, right, 180 degrees, and it looks exactly the same. So if you do that with your, turn it upside down, you get the exact same graph. Okay? And so that's one characteristic of origin symmetry. Okay? The other characteristic of origin symmetry, right, given the graph, for any point on the graph, if you change the sign of both the x and the y coordinates, then that point is on the graph. So here's the point 2, 2. So I change the x coordinate from +2 to -2, and the y coordinate from +2 to -2. And you notice that the point -2, -2 is on the graph of this equation. And similarly, here's the point -4, -2 on the graph of the equation. So if I change the sign of both of those coordinates from -4 to +4, and -2 to +2, you'll notice that the point 4, 2 is on the graph. Okay. So for any point on the graph of the equation, you change the sign of both the x and y coordinates, and that corresponding point is on the graph, then you have origin symmetry. Okay. All right. Well, just like with y-axis symmetry and x-axis symmetry, we can test for origin symmetry, right, given an equation. We can test for origin symmetry like we did for y-axis symmetry and x-axis symmetry. So at the bottom of the page, we have the equation y equals x cubed. It's our original equation. Okay. So to test for origin symmetry, you replace y with -y and x with -x. And then when you simplify, if you end up with the original equation, then you know the graph of the original equation will have origin symmetry. Okay. So replace y with -y and x with -x. Okay. Well, -x cubed is 3 factors of -x, right? Well, negative times a negative is positive, and a positive times a negative is negative, right? So the product of an odd number of negatives, right, is negative. And then we have x times x times x, which is x cubed. So this is -x quantity raised to the 3rd power. This is the negative of x cubed. Those are not, well, they're equal, but you should not view them as, it's the same, right? Students have to take a negative number and cube it in their calculator, right? often they forget to put it in parentheses. You gotta put it in parentheses. So this is equal to minus 1 times x cubed, right? That's what that is. This over here is minus 1 times x raised to the third power. Not identical. It's not exactly the same thing. Okay. All right. So minus x raised to the third power is the negative of x cubed. So just to emphasize what we have here, minus y is the same as minus 1 times y, and the negative of x cubed is the same as negative 1 times x cubed, right? And now solving for y, we can divide both sides or multiply both sides by negative 1, right? And when we do that, negative 1 times y over negative 1 is equal to negative 1 times x cubed over negative 1. Negative 1 over negative 1 is 1, and so we end up with y equals x cubed. That's our original equation. So the graph of this equation has origin symmetry. And we haven't even graphed it yet, so we know that. Okay? Have a good weekend. I'll see you Monday.